Hello, this video is about the sum and difference formulas. I'll warn you right away that this video is probably going to be fairly long, but included in this video is going to be some information that you probably don't strictly need, but I think is important. Like for example, I'm going to show you the proof behind some of these formulas, and really you just need to know how to use the formula, not where it comes from. But I can't in good conscience just give you the formula without showing you where it's from as a math teacher. So I'm going to show it, but I will try to in the YouTube studio thing, try to set up little chapters so that you can kind of skip through different parts of this video if you don't feel that you want to watch them. That way it will hopefully cut the time of the video. I've just spent a good minute talking about how long this video will be. That does not bode well for the length of the video. Sorry about that. Let's start. So what are sum and difference formulas? Basically, sum and difference formulas are ways that we can find the cosine of the sum of two different angles. And why would we need to know that if we have if we can find the sum of the cosine of different angles? Well, for example, I can easily get the cosine of 45 degrees on a unit circle, and I can easily get the cosine of 30 degrees, right? It's square root of 2 over 2 and square root of 3 over 2. But the cosine of 75 degrees is not the sum of the square root of 2 over 2 and the square root of 3 over 2. You can try that on your calculator and you will find that it doesn't work. So how do you do this then? Well, in order to demonstrate how this is done, by the way, why would you need to know this? Well, what if I wanted to know the cosine of 75 degrees or the cosine of 15 degrees or something, and I knew information about the constituent angles. So for example, right, if I had 15 degrees and I knew about 45 and 30, then I could subtract those two to get 15. So how does it work? So here's how it works. I'm going to try my best to make this proof fairly concise, but I'm gonna draw two diagrams here. Okay, this one and then right next to it another one. And I'm gonna have a couple of angles. So on the left one, I'm gonna have this. This is a unit circle. Okay, so I have a unit circle here. I just can't draw it. So assume the endpoint of that ray right there is on the unit circle, and we're gonna call this angle right here. We're gonna call it alpha. Actually, no, we're not. We're going to call that angle beta. Okay, then I'm going to have another angle over here, and I'm going to call that angle, that is alpha. And so hopefully then it's clear that the difference between these two, the angle between those two angles, kind of, is alpha minus beta. Okay, that angle right there. Now I'm going to say also that I know the coordinates of these points. So this point right here, because I'm on the unit circle, the coordinates of this point would be cosine alpha, sine alpha. Okay, this point over here, the coordinates of this point would be cosine beta, sine beta. And there exists a line that connects these two dots, and it has a distance of d, a length of d, whatever. Okay, capital D, whatever letter you want there. Now I'm going to draw a very similar diagram on the next little coordinate plane here, but now I'm going to essentially rotate this whole little triangle here. I'm going to rotate it kind of down. So now that angle that was up kind of in the first quadrant is now just along the x-axis, and this angle right here, this is the green one, that's just going to be there, and so D now is right there, if that makes sense to you. And we can also label, so we know this angle stays the same, right? That angle is the same triangle, it's just rotated. So this angle is still alpha minus beta. And the coordinate points of this point are going to be now, right, now think about what this would mean. It's going to be the cosine of alpha minus beta, comma, sine of alpha minus beta. And this point right here, because it's a unit circle, this coordinate point is simply 1, 0. Okay, now what we're going to do is we're going to write a proof that talks about the relationship between the two distances of those purple lines, the two lengths of those purple lines. So they're equal. Okay, done. Job done. That's the proof. Just kidding, it's not. We're going to actually use the distance formula to describe those distances. So, what is the distance formula? I'm actually going to move this over because I know I'm going to run out of space. The distance formula says that the square root of the difference in the x values, the x coordinates squared, plus the difference in the y coordinates squared is the distance, right? So looking at the first diagram, so this will be like D1 and this will be like D2, so D1, D2. All right, they're equal. So we'll say that this is cosine of alpha minus cosine of beta squared plus sine of alpha minus sine of beta squared. That's the distance of the one on the left. Okay, one on the right. I'm totally gonna run out of space here. I hope it works out. We'll see. This one is the cosine, so we're doing x coordinates, cosine of alpha minus beta minus 1, right? That's this x coordinate minus this x coordinate squared plus sine of alpha minus beta minus 0, right? Squared. Okay, so now we're going to square both sides. We're going to square both sides of this equation, effectively just getting rid of the square root sign, okay? And we will continue on as if the square root sign didn't exist, because it doesn't. So now we're going to square this quantity and square this quantity. So it's going to be cosine squared theta minus 2 cosine squared alpha minus 2 cosine alpha cosine beta plus cosine squared beta plus, now we're doing this quantity squared, sine squared alpha minus 2 sine alpha sine beta plus sine squared beta. I think I'm not going to run out of space. The equal sign is going to have to move over. Okay, now this quantity squared is cosine squared alpha minus beta minus 2 of 2 cosine alpha minus beta plus 1, and then this quantity squared is just plus sine squared alpha minus beta. Oh, it fit. Okay, awesome. So that's it, right? Now we can use this. I'm going to write down in the bottom left here something that we know because we've talked about this. It's the Pythagorean identity, that sine squared theta plus cosine squared theta is equal to 1. And so we kind of have a bunch of simplification to do here, because we have right here and right here, we have sine squared alpha plus cosine squared alpha. So that is just 1. And right here and right here, we have sine squared beta plus cosine squared beta. That is just 1. Okay? And then the only other things that we have here then are this minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. Okay, and that equals, oh wait, hold on, we have this and this, that's sine squared of alpha minus beta. Alpha minus beta is just an angle, call it gamma if you want, doesn't matter. So you would have sine squared gamma plus cosine squared gamma, that's just 1, right? Plus this original one, now we already had, minus what's the last thing there, 2 cosine of alpha minus beta. Okay, so now our equation is looking a little simpler. Let's combine like terms and stuff. So we have 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta equals 2 minus 2 cosine of alpha minus beta. We can subtract 2 from both sides. The 2's go away. Now we're left with, and let's see, hold on, let me write in another color, negative 2 cosine of alpha cosine of beta minus 2 sine of alpha sine of beta equals negative 2 cosine of alpha minus beta. I don't like negative 2, do you? No. So divide everything by negative 2, both sides, and you will end up with, and I'm just going to write this in the other way, the cosine of alpha minus beta is equal to the cosine of alpha times the cosine of beta plus, right, negative 2 divided by negative 2 is positive 1, right? So cosine, negative, these are now positive. Sorry, not cosine. Sine of alpha times the sine of beta. Now I understand that you are right now looking at this negative, that negative sign right there and this positive sign right there, and you're like, oh man, I don't like that. I don't like how they mismatch like that. And I'll tell you a secret, I also don't like that. But that's just the way it is, and we're going to have to be okay with it, okay? Okay, so this is the equation for the difference of angles for cosine. And you can apply the even and odd identity for cosine, which basically says, you know, cosine of negative theta is the same thing as just cosine of theta. And you'll get you'll get the other equation, which is the sum formula for cosine. So those are the formulas. You should 100% write those down if your teacher hasn't provided those to you. But that's really important. Now let's use them. So let's use them to find the answer to the question that we kind of started with. What is the cosine of 75 degrees? Well, the first thing we have to do is determine two angles that we already know everything about that will give us a sum or a difference of 75 degrees. Why not a sum? Sum is easier. I think it's easier to say, oh, 75 is just 30 plus 45. So we're going to write that as the cosine of 30 degrees plus 45 degrees. And we're going to just say for now that this is alpha and this is beta. So you can see now if we call 30 degrees alpha and 45 degrees beta, how you would go about plugging it into our formula. And it would look something like this. The cosine of 30 degrees plus 45 degrees is equal to the cosine of 30 degrees times the cosine of 45 degrees minus, ooh, there's that opposite sign. I hate it, but it's just the way it is. Sine of 30 degrees times the sine of 45 degrees. And we know all four of those things, right? So this is just cosine of 30 degrees is the square root of 3 over 2. Cosine of 45 degrees is the square root of 2 over 2. Minus the sine of 30 degrees is 1/2. And the sine of 45 degrees is the square root of 2 over 2. So we can do this. We can multiply fractions. This is going to be the square root of 6 divided by 4 minus the square root of 2 divided by 4. And that's the answer. It's sometimes written in a couple different ways. You can factor the 1/4 out of each of those fractions and leave what's left over would be this. So sometimes you'll see answers presented like that. Sometimes you'll see answers presented like this. Square root of 6 minus square root of 2 all divided by 4. All of those answers are the same. Ask your teacher about their preference for how they would like it presented. But that's the answer to this, and it's an exact answer. You don't have to round. You don't have to use your calculator. How wonderful is that? Let's look at another example. Okay, now, radians can sometimes be a lot trickier. Okay, pi over 12, just so you know, is half of pi over 6. So we're talking about a 15-degree angle here. But let's try to get away from the idea of having to convert between radians and degrees in order just to work with radians. Let's instead think about the normal radians angles we know. So for example, pi over 6, right? We know pi over 4. We know pi over 3. And if I were to convert these into pi's over 12s, well, pi over 6 is the same thing as 2 pi over 12. Pi over 4 is the same thing as 3 pi over 12. And pi over 3 is the same thing as 4 pi over 12. So hopefully you see then that if I took like any two of these and subtracted them, basically, like let's say I took 4 pi over 12 and subtracted 3 pi over 12, I would have pi over 12. I could also just say, what if I had 3 pi over 12 and 2 pi over 12? Subtract those, you'll get pi over 12. So let's do that one actually. So we know actually in secret, like secretly, these are the samesies, right? So we're going to do this. We want to find the cosine of pi over 4, which that's 3 pi over 12 minus pi over 6. That's your 2 pi over 12, and that will produce a difference of pi over 12. So we're going to use a difference formula here. We want the cosine of pi over 4 times the cosine of pi over 6 plus sine of pi over 4 times the cosine of pi over 6. And we can do all four of these things, right? The cosine of pi over 4, square root of 2 over 2. The cosine of pi over 6, square root of 3 over 2. Plus sine of pi over 4, square root of, sorry, I did a typo over here. That's a sine. Okay, sine of pi over 4, square root of 2 over 2. Sine of pi over 6, 1/2. So this is the square root of 6 over 4 plus the square root of 2 over 4. And again, you can write that as 1/4 times the square root of 6 plus the square root of 2. Or you can say it's 1/4, sorry, you can say it's, what's the thing we said? The square root of 6 plus the square root of 2 all over 4. All those answers are the same. And you'll notice it's very, very similar to the previous one. And that's because usually when we're coming up with these 15-degree increment angles, they're pretty similar answers. Okay, so we haven't talked about sine yet, but there's a really close relationship between sine and cosine. Effectively, sine and cosine are basically the same thing. They're just shifted, 90 degrees from each other, or pi over 2 from each other. So if you apply that idea, you get these two formulas for the sum and difference formulas for sine. You should write these down if your teacher doesn't provide them for you. Right? Let's try a problem with sine. Okay, so sine is 7 pi over 12. Again, when we're dealing with radians, we got to figure out, right, we can subtract two angles to get 7 pi over 12, or we can add two angles to get 7 pi over 12. I know that if I took 3 pi over 12 and added 4 pi over 12, I would get 7 pi over 12. 3 pi over 12, that's the same thing as pi over 4. And 4 pi over 12, that's the same thing as over 3, right? So I'm going to add pi over 4 and pi over 3 to get 7 pi over 12. The sine of pi over 4 plus pi over 3 is equal to, and just follow this idea, right? We're going to call this alpha and this beta, so anytime I see alpha and beta, I write them, right? So we've got sine of pi over 4 times the cosine of pi over 3. So notice how this one switches between sine and cosine, and very satisfactorily, I guess, it has a plus also. So plus plus. So that's nice and consistent. Love that. Okay, now we've got cosine of pi over 4 times the sine of pi over 3, and we can do this. So sine of pi over 4, square root of 2 over 2. Cosine of pi over 3 is 1/2 plus cosine of pi over 4, square root of 2 over 2. Sine of pi over 3, square root of 3 over 2. Okay, so this ends up being something, right? Square root of 2 over 4 plus square root of 6 over 4. You're seeing here probably a pattern where if you're not getting an answer that looks awfully like that, you're doing it wrong. And that's true. Okay, so there's your answer, and you can present it in whatever form your teacher prefers. All right, here's a little bit different of a question, and for this you have to remember your cofunctions. So remember, if we have a triangle, here's a right triangle, and let's say let's just actually apply numbers to these. So let's say this is a 30 and this is a 60 degree, and that's a right triangle. Well, I could say, right, if I'm talking about the sine of 30 degrees, like let's call this A and this B and this C. The sine of 30 degrees is equal to A divided by C, right? Opposite divided by hypotenuse. Well, the cosine of 60 degrees is equal to so 60 degrees adjacent over hypotenuse is also equal to A over C. So when you see these, that means that these two things are the same. And you can calculate that. They're both 1/2, and they're actually 1/2. But it's the same as long as those two angles are complementary. So 30 and 60 are complementary. That means cofunctions of complementary angles are equal. So in other words, instead of sine of 60, I could write cosine of 20. And instead of cosine of 80, I could write sine of 20. So what is this? Cosine of 20, cosine of 20 times the cosine of 20. Did I do this wrong? Let's see. That's not 20, it's 10. I'm sorry, 10. That's what I did wrong. 80 plus 10 is 90. Sorry. So cosine of 10 times the cosine of 20 times minus the sine of 10 times the sine of 20. That's looking like the sum of cosine, right? Isn't it cosine of alpha plus beta is equal to cosine alpha times cosine beta minus sine alpha sine beta? So in this case, alpha is 10 and beta is 12. So what is the cosine of 10 plus 20? sorry, 10, alpha is 10 and beta is 20. Well, that's just a cosine of 30 degrees. I don't need anything fancy for that. The answer to this is square root of 3 over 2. Okay, so just a different way to think of this sort of idea. It's kind of working backwards in a way. Right, here we want to find the exact value of the cosine of 165 degrees. I've suggested using the sum, and so this shows you that you can use bigger angles too. So what two angles add up to be 165 degrees? Well, I mean, there's a bunch of choices here. We could say, so 165 degrees is equal to, you could say 45 degrees plus 120. But there's all other sorts of options you can choose here. You could have also said something like it's 150 degrees. Well, that doesn't really work. Wait, you could say, what else could you say here? Hold on, I'm having a brain fart. Give me a second. 100, you could say, ooh, maybe you can't really say anything better than this. Oh, you could say 30 degrees plus 135 degrees, right? So either of those two things add up to 165, and there's probably more that I am brain farting right now that I can't find. But it doesn't. But the point is, it doesn't matter. You'll get the same answer either way, or you will get an equivalent answer either way. So let's do this one because these are using some different numbers than we've been using. Actually, well, they're both the same. It doesn't matter. Let's just do that one. So I'm gonna call 30 degrees alpha and 135 degrees beta. So now we're going to go cosine of 30 degrees plus 135 degrees, which is 165, is equal to the cosine of 30 degrees times the cosine of 135 degrees minus the sine of 30 degrees times the sine of 135 degrees. So this is cosine of 30 degrees is the square root of 3 over 2. Cosine of 135 degrees is square root of 2 over 2 minus sine of 30 degrees is 1/2. Sine of 135 degrees is the square root of 2 over 2. So this ends up being square root of 6 over 4 minus square root of 2 over 4, or 1/4 times square root of 6 minus square root of 2. Now you're noticing all these are the same. Well, it's the same way. These are the same way. These increments of 15 degrees, essentially, of course they're going to repeat themselves, just like increments of 30 degrees repeat themselves, right? We see these same values of 1/2 square root of 3 over 2 and square root of 2 over 2 all over the entire unit circle. So it would make sense then that we would see similarly frequent answers when we're dealing with like these 15-degree increments like this. All right. Now, sometimes we'll see sum and difference formulas presented in a little bit of different ways. And what we need to do here is identify what these angles are. This is a little bit confusing because what we are given here are side lengths, a ratio of side lengths, and the location of the angle, but not the angle itself. So the key here is to draw the triangle. Okay, we need to hashtag DTFT. If you haven't seen the 3.2 video about what DTFT means, DTFT means just draw the freehand triangle. Freehand is not the F word that I would use there, but it's just DTFT. So DTF this T, okay? So the cosine of alpha is 1/2, and it says that alpha is between negative pi over 2 and 0. So that means it's in quadrant 4, and cosine is 1/2. Well, cosine is 1/2 when we have this situation, right? This is a negative 60 degree angle, right? Or you could just say that this is negative pi over 3. Okay, that's alpha. So this is alpha, all right? Now beta, do the same thing. Okay, beta is between 0 and pi over 2, so it's in quadrant 1. And the opposite side of beta is 1, and the opposite side is 1, and the hypotenuse is 3. I don't know what we do here. So that's 3, that's 1. Then I can use the Pythagorean theorem to find this other this other side length, right? So I don't know what this is. It was square root of 2. Oh man, the square root of it's 2 root 2, I think. Well, let's just check. Hold on. So we have 3 squared is equal to 1 squared plus b squared. So we'd have 9 minus 1 is equal to b squared. Yeah, so it's square root of 8, which is 2 root 2. So here we have beta, right? We don't know the angle of beta. We don't know what degrees or radians it is, but it doesn't matter because we don't need to know it, because really what we're doing when we're doing the sum and difference formulas is we're evaluating an angle to find the ratio of side lengths, And we only need to do that if we don't know the ratio of side lengths. We do know the ratio of side lengths for this because we know all the sides of this triangle that has an internal central angle there, beta. You could have done similar for alpha. We just happen to know that this one ends up being negative pi over 3. So that's very convenient. Okay, so we're going to find sine of alpha minus beta. So sine of alpha minus beta is equal to the sine of alpha times the cosine of beta minus the cosine of alpha times the sine of beta. So so alpha's over here. What's the sine of negative pi over 3? It's negative root 3 over 2 times the cosine of beta. So here's beta. Cosine is adjacent divided by hypotenuse. It's 2 root 2 divided by 3. Okay, minus cosine of alpha. Here's alpha. Cosine of alpha is 1/2. It was given to us already. It's like right here. Right? Cosine of alpha is 1/2. Sine of beta is 1/3. Easy. Okay, that's given to us too. Opposite over hypotenuse. So this is going to be something pretty gross. So this is 2 times the square root of 6. So negative 2 root 6 over 6 minus 1 over 6. So that's the answer. You could write that however you want. Maybe you want to write that as, I don't know, how would you write this? Negative 1/6 times 2 root 6 minus 1. However your teacher prefers, but that's the answer there. Okay, and then the last one, cosine of alpha plus beta is equal to, write out what it is, cosine of alpha times the cosine of beta minus sine of alpha times the sine of beta. So that's going to be, what's the cosine of alpha? It's given to us, it's 1/2. What's the cosine of beta? We already found it over here. It's 2 root 2 over 3. So we're multiplying those together. Sine of alpha is, what did we say the sine of alpha was? Negative root 3 over 2, right? So negative root 3 over 2, and then the sine of beta is given to us as 1/3. So this is 2 root 2 over 6 plus, because negative times negative is positive, root 3 over 6. So this one is going to be, however you want to do this, 1/6 times 2 root 2 plus square root of 3. And so there's your answers. It is a little bit complicated, but if you draw the triangle, you're able to determine all the side ratios that you need using the Pythagorean theorem or just by knowing what the angle is. All right, let's look at a slightly different problem. Okay, actually, another one of these. I'm not going to do this one. You can pause the video here and do it yourself. The way that this would work, right, if you have sine of alpha is 3/5 and you're in quadrant 1, that's what that says. That means that this is 3, this is 5, and this is 4. And so you could find any sine, cosine, sine or cosine of that angle alpha right there, no problem. Okay, beta, cosine of beta is 2 root 5 over 5. So that means that, and we're in quadrant 4, so the adjacent side is 2 root 5, and the hypotenuse is 5. So figure out what this is, and then go from there. So go ahead, and if you want to impress me, you can post in the YouTube comments what the answer to this one is. But follow the same steps, right? So sine of, I remember what they said, you should have wrote this down before, but sine of alpha minus beta is the sine of alpha times the cosine of beta minus, minus cosine of alpha times the sine of beta, and then just plug these in and multiply together and you got it. Same thing for cosine, but use the cosine, sum of cosine. All right, let's look at a different kind of problem. All right, here we go. So this one's a little confusing. Now we have inverse trig going on. Something that's important to remember about inverse trig is that if you have, this is like an inverse trig thing, like the input to an inverse trig problem is a ratio of side lengths, but the whole thing itself is equal to an angle, right? So essentially what we have here is an angle alpha and an angle, an angle beta, right? And so we just need to figure out what that angle alpha is and what that angle beta is. And there's a bunch of ways you can do this, but these particular values are really pretty easy. You could draw a triangle here, but there's no point, because if I asked you sine of what angle is the square root of 3 over 2, and you're familiar with how inverse trig works, you know that the only angle that this could possibly be is pi over 3. Okay, And if I ask you the same way, if I ask you what angle, cosine of what angle gives you a value of 1, there's only one possible answer that will come out of an inverse cosine function, and that is 0, right? 0 radians. So this is really just saying what's the sine of pi over 3. And so the sine of pi over 3 is the square root of 3 over 2. And so that one's pretty straightforward. What if we had a slightly more complicated version of this problem? I'll show you how to do that. Okay, so this is vastly different in that we have alpha and we have beta, but these are not unit circle things at all. So what do? Well, if we're not sure what to do, we DTFT. Okay, so DTFT, tangent inverse of 5/12. Well, what is that? That means there's an angle that exists, and the side that's opposite the angle is 5, and the side that's adjacent to the angle is 12, and this is a 5, 12, 13 right triangle. It's a Pythagorean triple. If you didn't know that, you can use Pythagorean theorem to find that hypotenuse length of 13, and so this is talking about alpha. And then over here, let's draw beta. So beta is -3/5. If we have a negative ratio of sides for sine inverse, that means we're in quadrant 4, and we have the opposite side is 3, the hypotenuse is 5, which again, because this is a Pythagorean triple, means that the adjacent side is 4, and this is talking about beta. And so we are asking here for what is cosine of alpha minus beta, which is equal to the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta. And so we have all the information here. We don't know what alpha and beta equal, but we don't care because we just need the side length ratios. So look, cosine of alpha, here's alpha, cosine is 12/13. It's adjacent over hypotenuse. Cosine of beta is adjacent over hypotenuse, 4/5. Plus the sine of alpha, opposite 5 over hypotenuse, 13. So 5 divided by 13 times the sine of beta. So sine is -3 over 5. So -3/5. All right, so what is this? Well, it's 48 divided by 13 times 5 is 65. Minus, because 5 times -3, minus 15 65ths. So the answer to this is 33 65ths. That is the answer to that's like this, right? It's a strange question to ask, but that's how it's done, right? There shouldn't be you have to recognize that these inverse functions are giving you angles, and you just have a difference of 2 angles here. Yeah, now we're not going to go through any examples for tangent, but it's done essentially the same way. We just have different formulas. So if you encounter, tangent of different angles, well, just figure out what those 2 angles were that you had to add or subtract together to get the angle you're looking for, and then plug into these formulas. The proof for this is not really that bad, but I'm not going to show it on here because this video is already like 35 minutes long. Seems longer than that, am I right? LOL. Anyway, that's really it for sum and difference formulas. They're really quite versatile, and you'll encounter something coming up in this chapter called double and half angles. And what's interesting is that for the most, not in every situation, but in many situations, you can use either sum or difference formulas or double half angle formulas to find answers, and you'll get vastly different looking results, but if you plug them in your calculator and hit enter, you'll get they're the same answer. They just look really different, and that's kind of interesting to me because I think there's an easy way to do those kind of problems and there's a hard way to do those kind of problems, but it is useful to be familiar with both. Okay, that's all I have to say about that. I hope you enjoyed this video, hope it was instructive, and I hope that I'm able to put the little bookmarks in it so you don't have to watch the whole thing if you don't want to.